right. Good morning. Happy Friday. So I had a brief power outage. I saw the lights go out and then they came back on, but it killed my desktop yesterday. So I want to just pick up where we left off yesterday. And there wasn't really much more that I wanted to do, because once we have the expected counts, then we can find the observed minus the expected. We can square those, right? But now we have more of those differences that we need to square and then sum up, right? I guess we divide by the expected value first, right? But so each cell, right? If we have a 3x3 table, then we're going to have 9 expected values that we need to calculate, right? What's nice is notice how it takes the row I total, right? And so it really just takes the row total and then times the column total and then divides by the table total. So you don't have to worry about the individual cells necessarily, right? You're just looking at the totals to get your expected counts, okay? So for example, if I have, I didn't bring in an example. Okay. Let's see here. I feel like there was something I wanted to finish saying here when it cut out. I was cut off. Let me go back there. I was saying we have the row total. Oh yeah, okay. So, so really what we would do is if we have 140 people, I guess, in category 1, right, for variable 1, then we could take that and divide it by the table total, right? Because that's the proportion that we would expect for all of these guys, right? The row total. And then when we multiply it by the column 1 total, because that's how many are applied to that percentage, okay? Kind of doesn't really make sense, I guess, unless you do an example. So let me see if I can grab one here. I just want to work through, oh, why is it so high up? Okay. I just want you to see a table. Oh. Okay. Just going to grab this table. Let's not care too much about what's going on here. I just want to show you how to calculate those expected values, because once we're able to, so here's kind of, that's from last day. Once we have calculated the expected values for each cell, right, then we calculate the chi-squared test statistic the exact same way that we did before, right? So then we're in the exact same environment. It just depends on where we started, right? Do you have just one variable with multiple categories that you want to look at, right, and compare to some distribution, okay? Or do you have 2 variables that you want to compare? Are they independent of each other? So once we have calculated the expected values for each cell, we calculate the chi-squared test statistic the exact same way that we did before. We calculated, past tense, we calculate the chi-squared test statistic the same way we did before. Okay. To find the p-value, right, we need to use the table. So we need to use the table, but we need our degrees of freedom. So now we have a 2x2 table. So the only new thing that we need to introduce before we can kind of leave this alone I'll show you how to calculate those expected values, but then you're pretty well good to go. So the degrees of freedom are going to be slightly different because we have two variables, right? So to find the p-value, we need the degrees of freedom and for a 2x2 table, for a 2x2, oh, I don't know why I said 2x2. That for a two-way table is what I meant. I guess I wasn't that far off. Got to cut me some slack. It's early morning still. So for a two-way table, the degrees of freedom is, and let me just confirm here. Yeah, it's the number of rows minus 1 times the number of columns minus 1. So usually what we write is we write a capital R minus 1 times a capital C minus 1, where the R is the number of rows and C is the number of columns. Okay, I'll say or. Okay, so we're going to have slightly more degrees of freedom here because we have more variables to look at, right? And so we might make use of the larger degrees of freedom part of our table, but I mean, even if you have a 4x4 table, you would still only have 9 degrees of freedom, right? 4 minus 1 times 4 minus 1, 3 times 3 is 9, right? So you still don't get a huge number of degrees of freedom. So we're usually restricted to the top part of the table. Okay. Okay. So after you have found the degrees of freedom, the procedure stays the exact same as it did when we first introduced the chi-squared test. Okay. The procedure is exactly the same as before. That's what's confusing in the beginning, right? Because we want to work through all of them. But what's going to happen is I'm going to let you fly on your own a little bit. Okay, so I need to introduce, so my job is introducing you to, okay, so here's a Z test, here's a chi-squared test, here's a T test, it's coming, right? Here's an F test. But as long as you know what the hypotheses are and what the test statistic is and how to find the p-value for it, after that, you're good to go, right? You know what to do if you find a small p-value, then you have enough evidence to reject H naught, and that's always going to be the same, right? And so here we're building up this library and it feels overwhelming, right? But just remember, it always follows the same core structure. Okay, so I do want to show you how to find expected values, right? Let's see here. So each cell, let's see if I can make it bigger here. So we've got the totals. Oh, jumped around. There we go. Okay. So what we're going to have is we're going to have E11, and you can have a little comma. You can even wrap it up in brackets if you want. We're going to have E12, E13, E21, E22, and E23, right? So we're going to have 6 expected values, right? Because we've got a 2 by 3 table, the totals don't count, right? Well, technically the total is a count, right? But no, but they don't do anything here. That's what I'm saying. Okay, so to find, let's see if I can keep it on the same page even. Crop, move it up. Okay, to find E11, if we go back to our calculation, right? Now, I is 1 and J is 1. So we take the row 1 total times the column 1 total divided by the table total. Or I actually don't really tend to use this so much because I just look at the totals that correspond to each cell, right? And then I multiply those and divide it by the table total, right? And you can play around with it to convince yourself that that makes sense, right? But if we're testing for independence, then if we have 61 people out of 219 in this disclosed problem, right? And we have 73 in each of these columns, then we would expect the count to be evenly distributed across the disclosed problem, right? And so that's, you can read the textbook. It's got this, you're buying an iPod, I guess, with problems. And anyways, some tests they did. So here, what you would have is 61. Technically, you would have 61 divided by 219 and then times it by 73. But multiplication and division, we can smush them together and it looks a lot nicer if we just take 61 times 73 divided by 219. 61 times 73 divided by 219 puts me at 20.33 repeating, right? You can round to 2 decimal places. Unless you get a real decimal place, then keep all your decimal places. The reason for that is because you need it to add up to 61 at the end, right? So you need your expected values to still add to 61 and in general add to 219. So you don't want to be rounding, right, unnecessarily, right? Even if you round this, you might have to absorb that rounding into some of these other values. Okay. So here we're expecting to see 20.33, but we only saw 2, right? So that gives us some idea that, okay, well, maybe there's not independence here. So I'm already leaning towards being able to reject H naught, right? Because H naught is always a statement of variable 1 is independent of variable 2. Okay. So if we do E12 is 61 times 73 divided by 219. They're not always the same, but the reason they're going to be the same is because we have 73 across the board here, right? So that's not always the case. Okay. It is often because that's how we lay out studies a lot of the time, right? But in this case, they're always the same. And then what if we did, just to show you another option, E23 is 158 times 73 divided by 219. Okay. Again, once we have an expectation for this row, then it's going to be the same because the row total is always the same. And in this case, the column totals are all the same as well. Right, so 158, oops, I did 159, that's not going to help. 158 times 73 divided by 219, 52.66 repeating. So you'd have to do some rounding, but you want to be really careful that they still add up to the same values. So you will need to round the expected values, right? Maybe 2 decimal places is usually okay, right? Just make sure that the totals remain the same. So the totals for the expectations remain the same. Make sure the totals remain the same for the expected values. Yeah. So then, once you have your expected values, you can calculate your chi-squared. Your chi-squared is the observed minus the expected for each of the cells, then square it, right? And then divide by the expected value, and then sum all those up, right? So then calculate chi-squared, which is the sum of the observed minus the expected squared divided by the expected, with degrees of freedom equal to r minus 1 times, times c minus 1. I usually don't like to use the x multiplier, but in this case, there are no x's involved, so I'm going to do it. But just as a side note, if you are talking about x's in your equation, then you should not use the x multiplier. But in this case, it's obvious that it's a multiplier, so we're fine. Okay, good. I feel like I would have finished that with a little bit of time that I had left, but all right. So I'll leave that with you, the chi-squared. And what I want to do is I want to start introducing a new test. It's called the t-test. And now we're moving into numerical data, right? So if you want to test the average of something, so usually if you have numerical data, we want to talk about the average. We want to learn about, okay, is this average that I've observed, is it extreme or not, right? And so has there been improvement, right? That would be an extreme value. Has there been a significant decrease? Do I see a significant difference here, right? And so now we're going to move to talking about numerical data. Okay. So chapter 7, I feel like I should start it on a fresh page. It's a whole new chapter. Whee! I tried to keep that on the old page, but couldn't pull it off. So chapter 7 is inference for numerical data. I did it. I'm going to squeeze a little bit of chapter 7 in there. Not bad though. And what I'll do is I'll put some practice problems up. Yeah, I don't think we'll even finish 7.1, but we might. What's really fun is the mean is, so basically when you're out in the real world, you're either going to do a test of proportions or a test for means. And so once we've introduced the means, then you'll have kind of a complete toolkit and everything else is just extra. Okay, so inference for numerical data. All right, and so it's really important, and I guess I flubbed it there. Numerical data, this is new, right? We haven't seen numerical data before. We've been talking about categorical data, right? Because we're talking about the proportions. So now we're analyzing the mean. Okay. Just like before, right, when we talk about inference, so what was nice with the chi-squared is there were no confidence intervals involved, right? We were just doing hypothesis tests, just full-blown hypothesis tests, right? State your hypotheses, do the test, find the p-value, state your conclusion. We're still going to do that for the means, but we're also going to be able to build confidence intervals again, okay? So, and then of course, just as a reminder, inference is really just hypothesis testing and confidence intervals. Okay. I did post some notes, but they're probably called chapter 5 because that's the old chapter. And they do refer to when we used to do a Z-score for the means, which we don't really do anymore. I kept it for the example. I want to show you the example and some of the R code for that example. So that's why I kept it, but we're gonna freewheel here. Not really, but so chapter 7, 7.1. One sample mean. I don't think that's what it's actually called, but that's what I'm going to call it. Okay, so remember, we're always going to want to, when you read a question, you have to identify what type of question it is. Okay, and so the types that we've seen so far are one sample proportion, right, where you have a proportion and you want to compare it to a value, right? And maybe that's what I'll do a little summary here. Cut, remember I wrote that. So far, the question types we have seen are one sample proportion, one sample proportion, and now I'm going to get really wild and crazy here. And what I'm going to do is I'm going to show the null hypothesis beside each of them, right? Because that shows us what's happening, right? So one sample proportion, well, I'm comparing a proportion to some hypothesized proportion, right? And so H naught is that P equals some P naught, right? Some null value. We've seen two sample proportions. Okay. Which was that H naught is that P1 P1 minus P2 equals 0, or P1 equals P2, it doesn't matter, or P1 equals P2. Those statements are equivalent, right? So whichever one you prefer, just go for it. Okay. And then more than two sample proportions, right? So then we can talk about more than two proportions. The null hypothesis became a little bit weird, right? But that's when you do a chi-squared. And the null hypothesis is the data follows the hypothesized distribution. The data follows the hypothesized distribution. And then if we want to compare two categorical variables, so each of those would have proportions, right? So compare two categorical variables chi-squared, right? That's also the chi-squared. That's the one that we finished. And we said the null hypothesis is that variable 1 is independent of variable 2. So now it's a test of independence. We can still do a test of independence here, but then the independent distribution would be the hypothesized distribution. Okay, so in general, we call this a goodness of fit test. So here, this is called a goodness of fit, or maybe here. Goodness of fit test. Whereas if you're comparing two variables, two categorical variables, right, then the null hypothesis is that variable 1 is independent of variable 2. Which is called a test of independence. Yeah, and you know what? I left all this blank space. How about I shove that list up above? Because oh, now I cut it. Oh well. Because I want to, because I want to. You guys are probably too young. There was an artist named Billy, and she had this one-hit wonder, and it was all like, because we want to, because we want to. Anyways, it's called Because We Want To, I'm sure. So anyways, let's get back. So here's the types of questions that we've seen so far. And I'd love to know if anyone remembers the song. It might have just been in Europe, but yeah, because you want to test, because you want to, because you want to. Yeah, so these are the types that we've seen so far, right? We've seen 4 different types. We could introduce a lot more types, and that's what we're going to do, okay? And so the next type of question is going to have to do with, so no longer proportions, right? So these are all having to do with proportions. So these are all proportion type of questions. And remember, proportions have to do with categorical data, right? So now we're moving into numerical data. Maybe I'll highlight that here. Whoops. Categorical data. Okay. So we've done categorical data, and it'll come up, but those are the main tests that we do for categorical data. And now we're going to focus on numerical data. Right, so here we have numerical data, which means we're going to be analyzing the mean. So our hypotheses and our confidence intervals will all be about the mean. Okay, so here, I guess I wrote it out, but then I managed to copy over it, so oh well. 7.1 is a new type of question, and I'll just say the type here is one sample mean. Just like in the one sample proportion case, we have a sample mean that we need to compare to some hypothesized mean. Okay. So just like the one sample proportion case, we now have one sample mean. So we've taken one sample and we've calculated the mean because it's appropriate because we have numerical data, right? So we have one sample mean. What's annoying and also useful later on is that every word that we say matters, right? One sample mean, all of that. So one just indicates, and then one sample, of course, indicates that we've taken one sample. So there's clues all along the way. But usually when we first read these things, we just read it as one sample mean and we don't absorb what we're saying, right? But there are a lot of clues along the way, right? The mean means we have numerical data, right? And so now we have one sample mean that we want to compare to a hypothesized mean. Okay. Remember, we can do a lot with the standard error, right? Or maybe first a quick reminder, right? Recall that X bar, because it's been a while, X bar is the sample mean. Okay. Just like in the one sample proportion case where we had a sample proportion and we wanted to compare it to some hypothesized value, right? That's going to be our null value. And so we're going to have a null value here as well, right? And so, and most importantly, mu is the population mean. So all our hypotheses and our confidence intervals are trying to learn about mu, right? But we use X bar as a representative, right? As a temporary representative. Okay? And so we are trying to learn, to learn about mu, the population mean, right? And so what's going to happen is our null hypothesis is going to be that mu equals some mu naught. Okay. So for example, our null hypothesis is that mu equals some mu naught, where mu naught is the null value. Or if you prefer to think of it as the hypothesized value, right? The value that you want to compare your sample mean to, that's the mu naught. Okay. And then just like in the one sample proportion case, right, we could have mu not equal to mu naught. That's the default. Okay. Or we could talk about, right? Or we could have less than or greater than, right? Depending on the question. Depending on the question. But not equal to is still the default, right? So if you're not sure, then not equal to is still the default. Okay, that's always the case. Okay, so if you don't want to bother with the less than, greater than, because it can get you into some trouble sometimes, because if you find something interesting on the other end, you actually can't talk about it, right? So if you state that mu is less than 5, let's say, I shouldn't use 5, it's coming up in our example, but probably next week, so whatever. 10, let's do 10. That's so different. If I say that mu is less than 10, and then I take a sample and I find a sample mean of 12, well, 12 is not less than 10, right? But maybe I want to know if 12 is significantly more than 10, right? So if I do a not equal to, then I've covered both sides, right? So that's why it's the default, because it's the safest one. And you can only talk about a difference, right? But that's better than not being able to talk about something interesting at all, right? So that's the logic. So, but not equal to is still the default. Okay. Lots of stuff going on here, but it's all review, right? If I have a less than or a greater than, then I have a one-sided test. Whereas if I have, look at this, double up. If I have a not equal to, and maybe I'll do it around the other one here. Not equal to, then I'm concerned with, is there a difference? So I don't care which side it went to, right? Then I have a two-sided test, we call it. Okay. So we're going to have the sample mean. Now, the sampling distribution of X bar is, well, I should write it down. The sampling distribution, because remember, it's been a while since we needed things like the standard error of the estimate, right? And so the standard error of p hat and the standard error of p1 hat minus p2 hat, for example, right? But those are all components that we use to build our hypothesis test and our confidence intervals. Unlike proportions, and I'm thinking, well, both of them actually, the standard error stays the same regardless of if we're doing a hypothesis test or a confidence interval. So it simplifies greatly. And there's way fewer assumptions that we need to check. And a lot of them are kind of wishy-washy. So often I don't even bother saying them, and that's lazy of me. So we will talk about them, but usually as long as your sample size is over 30, you're good to go, okay? And so that's the long and short of it all, but let's get back to the sampling distribution of X bar. Is X bar follows a normal distribution centered on mu with a standard error of sigma over root n. Okay. So what we're going to have is the standard error of X bar. Because I don't have sigma, I'm going to use the next best thing, and that's the sample standard deviation, S. Okay. We don't know sigma because remember, sigma is the population standard deviation. So if you think about it, if I'm trying so hard to learn about the population mean, but I happen to know the population standard deviation, what happened? Did I go out and collect the entire population and then I threw it back in the pile? And now I'm frantically trying to figure out what the mean is? No, that makes no sense, right? So I'll never have sigma. So we don't know sigma. So we use the sample standard deviation instead. So we use the sample standard deviation instead. S instead. And maybe I'll shorthand this so that it all fits instead. There. Okay. So the standard error of X bar is S over root n. Okay. That's nice. That stays the same regardless of if I'm doing a hypothesis test or a confidence interval. Okay. Stays the same because remember, for the hypothesis test, we use the null value for proportions, and then for confidence intervals, we use the sample proportion. So that can get confusing, right? And then we ended up using the pooled proportion. So here it stays the same for hypothesis testing and confidence intervals. So for hypothesis testing and confidence interval. Okay. The test statistic that we use, right? If we think about a test statistic in general, is the point estimate. I'm struggling for the word here, right? How do we find it? We find the point estimate minus the null value divided by the standard error of the point estimate. In this case, the point estimate for the population mean has to be the sample mean, right? The point estimate, for the population mean is the sample mean. Okay. The null value is that mu naught, right? We already established that, okay, here, my null hypothesis has to be that mu equals some hypothesized value mu naught, right? And so what I'm gonna have is I can replace this point estimate with X bar, okay? X bar. And then I can replace this null value. The null hypothesis is that mu equals some mu naught. So then this mu naught goes here. And we already said, try to use all my colors here, the standard error for X bar, because that is the point estimate, is S over root N. The test statistic is a T. It's a T-test, and you might have heard of T-tests if you're reading studies and they involve numerical data, which they often do, then they'll say, oh, we did a T-test. Well, of course you did. It's all we do ever. So the test statistic itself, let's see if I have a different color here. Haven't used orange. Orangey glad. The test statistic is a T-test. So we've developed that T must be X bar minus mu naught over S over root N. And maybe I'll clean that up a little bit. S divided by, well, it looks the same, I guess. What's interesting about T is it's very, very similar to a Z, right? It has a bell curve, okay? But the problem with the normal distribution, the Z distribution that we're so used to seeing, is that the only thing that we're estimating is the sample proportion, right? So the only thing we're estimating is the population proportion, right? Everything else follows from that. But now I have two pieces of information that I'm pulling from the sample, right? So they're sample dependent. So even if I pull a sample of the same size N, right? We understand that if I take a random sample of size 40 and I calculate the mean and the standard deviation, those would be slightly different from if I put those guys back in and then I take another random sample, so still well collected, right? Random sample of size 40. Then if I calculate the mean and the standard deviation, they're going to be slightly different. They're going to hover around the same spot, but they're going to be slightly different. And so a T, to make up for that, has degrees of freedom, just like we saw with the chi-squared test. And so what's different about the t, and maybe I'll say the t distribution, the t distribution has n-1 degrees of freedom. Has degrees of freedom n-1. So df is n-1 in the one sample case. The degrees of freedom, how we find it, just like the chi-squared test, is going to depend on the type of question that we have, right? But for now, let's talk about the t distribution with my little bit of time remaining here. And so the t distribution has n-1 degrees of freedom, which means the shape of the t distribution depends on the sample size, right? And so here, what this is saying is that the shape of the t distribution, I'll put air quotes around the shape of the t distribution depends on the sample size. On the sample size. Let's see if I have, where do I have those? Okay. Where are you guys? Only because I can't draw this thing for the life of me. Should have drawn on it. And I want to grab the other one too. Got to bump it to the top. There. Too high. There we go. All right. We are ready. So the t distribution looks the same as the normal curve. So the normal is the z. Okay. So the normal is the dotted one here. What we see is that in general, and we don't know what degrees of freedom this is, but probably around 20 or so, what happens is there's more room in the tails. Now we have to really dig back and say, okay, well, what does the area under the curve represent? Well, it represents probability. What are we saying about these more extreme values then? Right? Then we're saying, exactly. So now we've got these fat tails. They don't stay fat for very long. They're only fat for small sample sizes. But what it means is it's increasing the probability of seeing something more extreme, because it's saying, hey, based off of the sample size this small, I don't know if this is extreme or not, maybe not, right? And so here, it just leaves more room in the tails. Leaves more room in the tails for small sample sizes. And the area in the tail, yeah, so this is what we're going to be dealing with. Unless we have proportions, then what's nice is they follow a Z distribution, right? And so here now we're saying, okay, well, if I have a small sample size, the probability of seeing something extreme is more likely, okay? And I'm all out of time, and I'll post a tiny assignment 10 with just a little bit of practice with the means, and then that's how much you can expect to see on the test. Okay, so something, it's just a tiny assignment though, just a little one, just for practice. Okay. If you have any questions, let me know. Otherwise, have a great weekend. And I'll see you maybe for the test on Tuesday.